Hello YouTube, today we're going to be doing another superposition problem and we're going to be trying to find the voltage in this circuit here, that voltage across that 3 ohm resistor, and we're going to use the law of superposition. So the law of superposition pretty much states that you remove all sources except for one and solve that circuit. Then you remove the other sources and keep one, solve for that circuit, and so on, depending on how many sources you have. So here we have 3 sources, 1, 2, and 3. So we're going to have 3 separate circuits we're going to need to solve. So for the first circuit, we remove 2 of the current sources and keep 1 of them. So we're going to keep the 15 ohm or 15 amp current source on the left. And the law of superposition says when you remove a current source, it just becomes an open source. So we can pretty much ignore that part of the circuit there. Now if we were to remove a battery, then that would become a perfectly conducting wire. But that's a little different. This one's just dealing with current sources. So we got our first circuit set up here. By simply ignoring the 12 amps and the 24 amps, we have our first circuit. Now let's look at our second circuit. If we ignore the 15 amps and the 24 amps, we remove those from the circuit, then we're only left with the 12 amp current source, and we have our other circuit here. And then let's remove the 15 amp and the 12 amp for our third circuit, and we would only leave the 24 amps. So pretty much you have noticed how there's one source for each of the circuits here, and all you do is solve 3 circuit problems as a single circuit and then add the results together depending on what you're looking for. Here we're looking for voltage, so notice how I labeled V1, V2, and V3. So the total voltage is going to be the sum of V1, V2, and V3. And that's how the law of superposition works. You break it up, you remove your sources, and then you combine everything all together. So let's look at each of the 3 circuits. So here's the first one. It's a simple, current source and resistors in series and parallel. So why don't we reduce this down a little bit. We can sum the 3 ohm resistors into, since they're in series, we get 6 ohms, right? 3 plus 3 is 6 on the right there. And instead of calling it V1, since we combined it, I'm going to call it Vx. And you'll see why a little bit later, because we kind of have V1 embedded in Vx. So next, to further reduce down the circuit, we have noticed that 3 ohms and 6 ohms are in parallel. So we know that 3 in parallel with 6 is 2, and that means we have our equivalent here. So we can find the voltage from V equals IR, Ohm's law, and we know that the current, notice how the current is flowing counterclockwise, so that's going to be the negative direction here in this case, and I'll explain why in a little bit. And then we multiply by our equivalent, which is 2 ohms, and we get 30 volts, negative 30 volts for Vx. But we're not looking for Vx, we're looking for V1. So how do Vx and V1 relate? Well, since we have a voltage divider, the current, or the resistances are 3 ohms, they're the same, so we just cut it in half since it's divided. And then that means we have negative 15 volts for V1. So be careful with that one, because we're not taking the total voltage here, it was only part of it there, so watch out for that. Because like I said, the 3 ohms and the 3 ohms are the same, and it's negative because current flows from high to low potential, and in this case we have a negative sign from the current source here. So that's V1. Let's look at our second circuit here. So let's find V2. So let's also reduce this circuit and find our equivalent. So we know that 3 ohms and 3 ohms are in parallel. It can be reduced, or are in series. So we can sum those together to get 6. But that also has the V2 embedded in there, and you'll see a little bit. Now the 6 ohms and the 3 ohms are in parallel now, so 6 in parallel with 3 is 2, and then that's our equivalent. So using Ohm's law, we got V equals IR, IS being the current source, and R equivalent being the 2 ohms there. So multiply those two together, 12 times 2 is 24 volts, but V2 and V are is not exactly this V here. We should have called it VY or something. So again, we have the same resistance flowing through, the same resistance flowing with the same current. So that means, kind of like with the voltage divider, you're going to have to half it again because they have the same resistance. So you got negative 12 volts here. So again, potential is the reason why it's negative, flowing in the opposite direction than how we put the signs of positive and negative convention. Cool. Then we got the third one. Third circuit problem. We reduce it down once more. So 3 and 3 is 6. So we get 6 ohms there. So they were in series. Now we got this circuit here is in parallel. 6 in parallel with 3 is 2. And then we have V equals IR, right? But notice how V3 was not reduced when we were doing the equivalent circuit. V3 stayed in the same place. So actually, when we find the voltage here, which is 24 times 2, we get 48 volts. And that means V3 is going to get the full voltage, because when we reduced the circuit into a single equivalent resistor, V3 was not, divided or hidden among those resistors. It was the exact resistor we were looking for. So that means we get the full voltage. So to summarize, we found our V1, which was negative 15 volts. We found our V2, which was negative 12 volts. And we found our V3, which was 48 volts. So we took this one circuit problem, divided it into 3 separate ones with one source, found the voltage that we were looking for each of the circuits here, and all we got to do by the law of superposition is sum them up. So V1 plus V2 plus V3 is 21 volts. So that's how what the voltage is across that 3 ohm resistor in the very first circuit in the above, the first problem that we were looking at. Cool, so that's how you use the law of superposition.